Let's talk about Hess's law. Change in enthalpy is well known for many reactions. It's not known for all, but it's known for many. It would be inconvenient, time-consuming to measure the change in enthalpy for every reaction in which we are interested. So there's actually several ways in which to estimate the enthalpy of reaction or the heat of reaction. Hess's law is one of these ways. There are published values for heats of reactions, and we can use the properties of enthalpy to use these published values to calculate an estimated heat of reaction for a reaction. So Hess's law, technically Hess's law states that if a reaction is carried out in a series of steps, the enthalpy for the overall reaction will be equal to the sum of the enthalpy changes for the individual steps. Delta H, change in enthalpy, is a state function, meaning it doesn't matter the path that you took to go from the reactants to the products. It only matters the distance from the reactants to the products. So the total enthalpy change depends only on the initial state, your starting point, and your ending point. It doesn't really matter where you go in between those 2 points, state function, initial state, and the final state of the products. I find it easier just to approach Hess's law by just looking at a problem. I'm going to make the font smaller here so I can actually work with it. Give me a minute. Okay, so the enthalpy for the reaction for the combustion of carbon to carbon dioxide is negative 393.5 kilojoules per mole of carbon, and the enthalpy for the combustion of carbon monoxide to carbon dioxide is negative 283.0 kilojoules per mole carbon dioxide. Let's look at this first reaction and draw it, or write the reaction for it. So I have carbon as a solid and oxygen, because it's a combustion, going to carbon dioxide gas. The change in enthalpy for that reaction is negative 3.93 kilojoules per mole. I'm just going to say kilojoules per mole because as written it is per 1 mole of carbon. And that's balanced. The enthalpy of combustion for carbon monoxide to carbon dioxide is negative 283.0 kilojoules per mole of carbon monoxide. So writing that equation, carbon monoxide is a gas, it's a combustion, so it's reacting with oxygen, going to make carbon dioxide gas. Delta H for that is negative 283.0 kilojoules per mole. Again, it was per mole of CO. I only have one CO, so I can write it like that. Now, is this balanced? Not quite, but if I put half in front of the O2, then that does balance it. What am I trying to find? Well, I'm trying to find the delta H for the combustion of carbon to carbon monoxide. So my target is carbon plus O2 gas going to CO gas. Balancing it would be a half there. This is what the reaction I am trying to get to by using these two reactions and these two enthalpy changes. It really is just a system of equations. Okay, so using these two reactions, multiplying them perhaps, reversing them perhaps, I'm going to try to add them to come up with my target. What am I looking for? How I do this is I usually look at what I want to end up with, and I notice that I have carbon as a product. In the equations given, I'm only given carbon in this one reaction. Carbon is a reactant in what I'm trying to get to. It's a reactant in this equation. So I'm probably safe in assuming that I'm going to write this first equation as written. So my delta H stays as written for that first equation. Now the second equation, I've got oxygen a couple places, so that doesn't help me. But my product is carbon monoxide and only shows up one place in the second equation. Shows up as a reactant. I want it as a product, so I am going to have to reverse this reaction. So I'm going to have its product as a reactant, and then have the carbon monoxide reacting with a half molecule of oxygen. The delta H, since I flipped this equation, the enthalpy of reaction for the reverse is just the opposite sign but the same number. So it's a positive 283.0 kilojoules per mole. When I add these two equations together, I should get this overall equation that I was targeting. If I look, my carbon dioxides will cancel. I have oxygen on this side and a half on this side, so that would make it a half. So overall I get carbon plus half of an oxygen molecule going to carbon monoxide gas, and then I just add the heat of reaction, so I have negative 393.5 plus a 283. My delta H for this reaction is negative 110.5 kilojoules per mole. Really is just a system of equations. Look at the equations that you're given, write your target, flip, multiply the equations given so that you end up with that. All right, let's try one more together. Here we have three equations. We're asked to use Hess's law to calculate the change in enthalpy for the reaction given here using these three. I start off the same way. I notice that carbon is a reactant. Looking in my equations, I notice carbon only shows up here. So it's a good guess that this equation is going to be written the same as it's written in my given information. But if you notice, I have a coefficient of 2. Well, I can just multiply everything in this equation by 2, including the enthalpy. Okay. Notice that the next thing is H2. It only shows up here. So it's a good bet that that equation is also going to be used as written, with the change in enthalpy negative 285.8 kilojoules. And there's only one hydrogen in the given, one hydrogen molecule in this equation, so I don't have to multiply by anything. So I've kind of used these two equations. I notice that my product is C2H2. Well, C2H2 only shows up here. It's a product in my target equation. It's a reactant in my given, so I'm going to have to reverse this equation. So 2 carbon dioxides from here, plus a water molecule in the liquid phase, goes to the C2H2 ethine, plus 5/2 O2 gas. Sorry, I write big. Change in enthalpy there is negative 1299.6 kilojoules. Let's add these things up. Cross off things that kind of show up on both sides. First thing I see is I have water on both sides. Ooh, I have 2 carbon dioxide molecules on both sides. And then the only other thing I have is oxygen on both sides. Well, this is 5/2. I didn't mean to actually write. Whoa, I don't know why it's writing like that. I'm sorry. Oh no. Oh, I'm having trouble. I don't, but if I, oh, I think I'm gonna have to start this over. Shoot. I don't think I can just get rid of one pen. I wish I would have hit that button earlier. Well, let me forge on. I'll try to write in green. But I had 5/2 here. I had 2 here and a half here. Well, 2 is 4/2. 4/2 and 1/2 is 5/2. Whoa, the oxygen cancels as well. Cool. So the only things not crossed out, if you can look through my scribbles where I was having tough technical difficulties, are my carbon, my hydrogen gas, going to produce my product, and my delta H is going to be 2 times a negative 393.5 minus a 285.8 plus a negative 1299.6. Uh-oh. What did I forget to do? My technical difficulty scared me, I think. Remember, I reversed this equation. So this must become a plus 1299.6. So it would be 2 times a negative 393.5 plus a negative 285.8 plus 1299.6. And that gives me a positive 226.8 kilojoules. So those are 2 examples of Hess's law. Sorry. We'll look at this one in class together, and then the next thing we'll look at is enthalpies of formation.